Hello and welcome to another episode of Flying High with Flutter. I'm your host, Alan Wyma. I want to give a quick announcement before we start this episode. I've already started up on a course all about how to integrate Rust in Flutter, and just so happens that our guest today is definitely in similar space as this, so it's good that we have her on around this time. Didn't plan this, it just kind of worked out, so I'm glad that you scheduled this time. But if you're interested in how to integrate Rust with Flutter, please check out rustwithflutter.com and sign up, and you will be getting some announcements. We should be having a Black Friday sale, so please sign up and you'll get that notice in your email. But anyways, back to the show. We have Lily Mara, who is a software engineer. Why don't you give a quick intro about yourself?
Yeah, thanks, Alan. I'm really excited to be here, and hi to everybody who's watching. I was a software engineer. I'm now an engineering manager at OneSignal here in the San Francisco Bay Area. We provide customer messaging solutions, and we use Rust in multiple of our backend applications, and it helps us to achieve really high throughput, really low memory needs. And the reason that I'm here today to talk with you, Alan, is I'm here to talk about my book, which is Refactoring to Rust, which is all about how you can take an existing software project and you can make it maybe faster or safer by identifying key components and rewriting just those teeny little pieces in Rust, those pieces where performance really matters or where safety is really important. I think, when you learn an exciting new language, you're maybe tempted to rewrite the whole world in that language, and it's just not feasible, especially for a project that has deadlines and constraints and all this stuff around it. So I think you can leverage yourself much more effectively by identifying the pieces where you have bottlenecks and trying to resolve those with Rust.
Yeah, I definitely agree with that. My first hankling with Rust was I've always kind of played with it, but I never really got too much into it. But I've always wanted to. And then finally I had a use case where I was parsing XML for a client, and I was using Elixir because it makes things much easier for concurrency, right? Mm-hmm. With the way they have their actor system set up. But then I noticed that it took about 10 minutes and gigabytes of RAM just to parse hundreds of XML files. And I thought to myself, you know what? I've always been wanting to use Rust, but then you always tell yourself, don't introduce a new technology to something,
right?
Because you may, be biting off more than you can chew. And that feeling was still there at the beginning because, when you're working with Rust, you have so many things. The borrow check is the biggest hurdle to kind of get over.
Yeah.
Yeah. But anyways, I'm very happy I did it because now I went from 10 minutes to processing down to about 10 seconds of total runtime for the whole thing.
Yeah, wow. That's a massive, massive difference.
Well, I only replaced one part of it too. So I went through several different parsing libraries in Elixir before I just said, okay, I'm going to use this parsing library for these bunch of files, but I'm going to use Rust for this one because it wasn't linear, right? The other one was parsing very linear, so I could just pattern match, keep going down. But when I had nonlinear, then it made much more sense, and it worked like that. It was amazing. I was super happy with it. That brought me on my journey to really getting more and more into Rust. Nice. And anyways, so this topic is definitely very near and dear to my heart because it's, I don't think many people, their first thing with Rust is doing FFI necessarily, unless I think it's one of the few people.
It's a scary topic, the common denominator for FFI generally is C, right? And I think that's where a lot of people get their first foray into FFI, and that's sort of what Rust and other languages like Go, Java, they tout that as a feature, we have good CFFI, and if everyone knows CFFI, then you can talk. However, I think most programmers are kind of scared of C, and especially with FFI, you're not just worrying about the memory model of Rust or the memory model of Java, you're also now worrying about the C memory model, which, as I think we're aware, is fraught with foot guns. So, yeah, it's a scary topic, but I think with just understanding a little bit more about how memory is laid out and you can do it without shooting yourself in the foot too hard. And I think learning Rust is especially helpful in that journey, because all of the rules of Rust, the borrow checkers rules, the single ownership, these are things that many, many well-structured C programs are already doing, but there's nothing to help you do them. It's just the programmer's responsibility to definitely not break the rules, I promise, as compared with Rust, where they're enforced by the compiler. So I think if you manage to internalize Rust's rules, then you can then move on to having the little bit less guardrails that you have with FFI without that being too scary, I hope.
Well, some of the backlash. So I tried talking to quite a few C and C++ developers about Rust, and I was like, yeah, this is amazing, because I knew about these issues like double free and use after free, just these kind of simple issues. And you kind of think to yourself, like, how do you not know that? But at the same time, I've never been a C developer, so I couldn't tell you about that. But since it happens so many times, it must be something it must be something that occurs more often than people really think about. And kind of going back to, like, why should I care about Rust when C has been around for so long and this kind of stuff? Like, why should I care about it? Why should I even bother to take a look at it if I'm already thinking I'm a good C developer?
Right. Yeah. I mean, you might be a great C developer. You might be the best C developer that's out there. But at a certain point, you are going to need to collaborate with somebody. And unless you want to spend inordinate amounts of time, writing documentation on ownership rules of functions and validating that all your collaborators are perfect C developers just like you, you're going to start to be limited or run into bugs. I mean, the main reason I think that folks should care about Rust is all of the companies that are noticing, hey, we're spending so much of our time, so much money on fixing memory safety bugs in C and C++ programs. I think Microsoft identified, 40-50% of security vulnerabilities in Windows in some recent year were related specifically to memory safety violations. And these are things that if you're writing Rust, you simply can't do. The compiler will not accept programs that have these bugs in them.
Sorry, I just wanted to butt in for a real quick. I think the number you gave is a little bit low. So I remember the number is 70%, but I wanted to verify the word. So from this article on, you can hear my keyboard. Yeah. So from the article actually on msrc-blog.microsoft, they say roughly 70% of the security issues that the MSRC, which I'm not too sure what MSRC is, I'm guessing
Microsoft Research Center?
Okay, I was brought down to you. You're the expert. But that makes sense,
I have no idea. I'm just guessing.
Could be. Anyways, so 7% of the security issues that MSRC assigns a CVE to are memory safety issues. So they said that this means that if software had been written in Rust, 70% of these issues would eliminated, which is crazy, right?
It's crazy, yeah.
I was just thinking else before I lost this thought in my head is do you remember this Israeli bug in iOS that happened recently? Sorry, when I say Israeli, I'm talking about there's an Israeli company that was exploiting a memory safety issue within iOS.
I don't remember that one, no.
Yeah, so this bug actually, it's funny that we hear like, oh, if you have a bug in your code, you can get somebody killed, but apparently this one actually got some people executed because they used the exploit to get into people's phones. Even the president, David, was it Macron, the guy from the heads of France? He also got infected by this one. So it was, I forget what it was called, but this was an issue both in iOS and also in macOS. Just before Monterey was released, they released a fix for it. But yeah, this stuff is scary.
Yeah, it's very scary. I was going to slightly temper us to remind folks that not every bug that exists is a memory safety bug. There are logic bugs, and you can write a logic bug in any language. If you say, drive 20 meters instead of drive 5 meters, or the Rust compiler won't help you with that. But when you do have memory safety bugs, the consequences are generally, as you just told us, very, very serious. So it's really nice that the Rust compiler can help us to avoid problems like this.
Just to kind of go back on what I was talking about, this one's called Pegasus.
Pegasus?
So
okay.
If you've ever heard of this one, yeah. And I think they said that this is also a memory safety bug, and I think somebody said that it could have been fixed with Rust. So this is kind of scary. I think also the Heartbleed was also similar, that it was also a memory safety bug.
Heartbleed was definitely a memory safety bug in OpenSSL a couple years ago that came to light. And that one could not have happened in Rust. And
I think there's another similar one that was affecting Intel processors only too, right?
So is that Rowhammer?
I forgot the name, but if I heard it, I would definitely remember.
Rowhammer or like Meltdown. There's something about melting.
Should be Meltdown. Meltdown, I think, is the one I'm thinking about.
Okay.
So that was also a memory safety issue, right?
I don't remember the nature of all of those different ones. There's too many giant vulnerabilities to keep track of, unfortunately. Yeah,
this one says it was a race condition. Because I think it's like the CPU does some like pre-processing before you actually need it in order to make things faster.
Right.
Yeah, Meltdown and Spectre were the two biggest ones.
That's right. I remember those. Yeah. So race condition is a pretty broad term. This can, like I said, this can be a logic bug, or it can actually be a memory safety bug if you're, not using protected memory access or atomics or something like that to access shared memory from multiple threads. So that piece of it, the piece of race conditions that is memory safety related, is also not possible for Rust. It's very safe and non-scary to write parallel Rust code, which is great.
In any case, I think the most important part to talk about is that even if you think this kind of issue is really important across all industries, right? Like you said before, even if you're great, you still have to collaborate. Well, even if you're not collaborating, you're still relying on something that somebody else made most of the time. Nobody's going out there making their own string library. If they are, good.
Right.
Congrats to them. That's going to take you some time. But in general, there's a lot of stuff that, Rust, I think, helps us solve. And I'm not saying go out there and rewrite everything in Rust. I'm not that kind of person, but
no.
Definitely consider that into your toolkit if you're going to be making something new. It's not just because the new hotness, right? It's about, there's a lot of things that you may overlook, and there's a lot of dependencies and stuff that you're going to be pulling in, and they may not be the most the OpenSSL is used by nearly every single web server out there.
Absolutely.
And that one was hit with a big bug that affected everybody around the world.
Mm-hmm.
So it's super scary that this kind of stuff can happen, but at the same time, we need to be aware. And I'm hoping that the stuff that is solid kind of stays solid, and stuff that is new can really be looked at in a new way. Maybe Rust is the solution, maybe not. I don't know.
Yeah, absolutely. And, even beyond the security implications like we've been talking about, I think Rust it does make programming, I think, more fun and more rewarding. I think the data structures and the facilities that are available to you as a Rust developer are really ergonomic. APIs are generally pretty easy to use because of the type system. It sort of forces you down the path of correct usage for most things, which is generally pretty helpful. And then something that I'm not sure if it's fully been exploited or tracked, but a theoretical performance benefit that Rust has over C actually is because of C's dynamic memory model and the way that it's just totally on the programmers to make all the decisions correctly. Many C libraries, when you pass them data structures, they actually have to make what's called defensive copies of those data structures. So many C libraries, if you pass a string to some library function, they'll actually copy the entire string because they have no way to validate that you don't later modify the string or deallocate the memory associated with the string, something like this. So, allocations are a very small, micro optimization for moving those, but in theory, Rust has some leeway where it could advance past C because of the stricter compiler rules.
But I think that's definitely true. But let's talk about because now you're making me remember about your book. So as I said to Lily before, she's one of the few guests who have actually had time to take a look and get into her book because we're doing the course, and I just want to make sure I'm doing as good as possible for you guys. But anyways, you had a really cool section where you're like passing a string, I think, from C to Rust, and you had this issue where not necessarily issue, but it was pretty interesting where you actually managed to make a string slice from that string and reuse the memory. But if that string slice was not UTF-8, this would fail, right? But I think we actually can catch that. So then we can probably then go back to OS string and try to get it that way.
That's correct. Yeah. So Rust strings are always UTF-8. That's like a constraint that's built into the language, and everything that uses a string type in Rust assumes that a string will always hold valid UTF-8. So this means that you only need to do that checking one time. So for example, if you're like you were just talking about, if you're reading a string into memory in C, there is no assumption about the encoding or the character set or anything like that that's used on the string. So if any function needs a UTF-8 string to work correctly, that individual function generally is going to be doing its own checking to validate that your string is UTF-8. So you're going to have lots of repeated checks. Whereas with Rust, if you have a string, an instance of the string slice type or a heap allocated string, it's assumed that it's valid UTF-8 because it has to be at construction time. And yeah, I think the method that I was using in there was str string from UTF-8, which returns a result, which is an enum of either a success case or a failure and the associated error. And so there again, we have the compiler is forcing you to deal with the possibility that this UTF-8 check failed. So you cannot possibly proceed past the UTF-8 check without checking on the result of this function call. You can't accidentally use a string that's not valid UTF-8. There are many, many different types of strings in Rust to sort of cope with all these various possibilities that exist. And I've seen a meme passed around a few times where one programmer is looking at a char pointer in C, and then the Rust programmer is looking at vecu8, char array, OS string, C string, heap string, string slice. There's all these, various kinds of string types that exist in Rust. And, similar to what I said about ownership rules, all of these different types of strings, they exist in C, and programmers need to be aware of these differences, but the language provides no facilities for helping you deal with them. So, take, for instance, the static string slice versus the heap allocated string in Rust. Those are two very different types. You can do read operations on both of them. Read operations work exactly the same way on both of them, but you can only write to a heap allocated string because it's the only one that has dynamic memory associated with it. That exact limitation exists in C for char pointer strings that are compiled into a binary, that you literally write as a string literal between double quotes, compared with, malloc strings that exist on the heap. But the language will just let you write to that static string that's compiled into the binary. And people are probably going to tell me in the comments that I'm wrong, but I believe it's undefined behavior if you do that. And, you don't want to, but the language will just let you. So that's a limitation that exists. You have to be aware of it. You should be reallocating your string if you're going to write to it, but the language will just let you get away with it.
I think that's a really good strong point to make about Rust too, is that they try as hard as possible to, I don't know if it's completely been all removed, but basically remove this thing about undefined behavior, which is, I think is super great, because if you are a great C developer, if you ask somebody, what happens on a double free? I don't think the guy could ever tell you, because like I said, it's undefined behavior. You don't know what's going to happen.
Right.
That's really interesting and scary, because those kind of situations happen.
Yeah, it's scary. I mean, you can trigger undefined behavior in Rust in unsafe code blocks or unsafe functions, but these are always like gated off. Like they always have the unsafe label around them. Generally, when folks are writing unsafe code, they'll provide like comments that describe, why the block is actually safe. And I think people have realized that it's a bit of a misnomer, the unsafe keyword, because really it just means unchecked. Like you shouldn't actually be writing Rust code that's unsafe or could possibly blow up at runtime. Like the checks should always be there. The difference is sometimes the compiler is not able to uphold invariants that your code needs in order to run. For example, if you're interfacing with C code, C doesn't care about Rust's memory model at all. So you have to call, a function like string from UTF-8, which takes in a U8 pointer and a length. And, you have to either do some validation to make sure that that length is the correct length for the U8 pointer buffer associated with it, or, you have to trust that the C code passed you the right length. And there's, not much you can do if it isn't. But all we're doing in unsafe blocks is we're turning off a little bit of the compiler's helping hands when we absolutely have to. And we can trigger undefined behavior in these blocks, but generally it is, the language works as hard as possible to stop you from being able to do that. There was actually a deprecated function, I think last year, maybe 2 years ago in Rust, in the standard library, the std mem uninitialized function was determined to be essentially impossible to use correctly without triggering undefined behavior. And so the language teams deprecated that function and created a new interface that will still allow people to create uninitialized memory, but will be safer for folks to use and will not trigger undefined behavior.
I think this happened recently, right? Because I remember hearing at least something similar about this, about uninitialized stuff. It's like I didn't quite understand what would be the reason that I'd want to like have data but not actually initialize it yet. I think it's upon use and it gets initialized. Yeah,
so it's kind of a performance optimization, like a micro optimization. So, for example, if you're a C developer and you use the malloc function to request a buffer from the operating system of memory, it's just going to hand you a chunk of memory, and it's not going to zero the memory. It's not going to put any particular value in the memory. It's just going to hand you a block of memory, and whatever data used to be there, you're just going to get. And if you don't clear it out, or you don't write valid values into that memory buffer, then you may trigger undefined behavior, or you may have some problems. That's fine for C. It works with C's memory model just fine. But Rust had an additional constraint on their memory model, which is the Rust compiler always assumes that if you have a T, like some type T, that there will always be a valid instance of that type in the memory that's associated with the value of that type. So that's kind of confusing. But if we think, for example, about a vector, which is, I believe a vector is two numbers and a pointer. It's and the order is probably wrong, but it's a capacity, so the total number of items that could fit into the memory buffer, a length, which is the number of items that are actually in the memory buffer, as well as a pointer, which is the pointer to the beginning of the buffer region. If we think about a vector, like there are certain invariants that need to be held there, like the pointer always needs to be a valid region of memory, and the capacity always needs to be greater than or equal to the length. Like you can't have 100 items in a vector that's only big enough for 2. However, if you constructed a vector using stdmem uninitialized, it might give you back a pointer to memory in the code segment, which is non-editable, and a capacity of 0 and a length of 20 billion. And I don't know what intrinsics are in the compiler, but it's possible that the compiler could emit code that runs incorrectly based on those assumptions, even if you don't actually use the vec to do anything. Like it's written in the behavior rules of the compiler. The compiler is allowed to make these assumptions, and so we have to uphold those assumptions.
I kind of want to go back to talking about strings for a second, because I think our audience is really interested in Rust, and so I think they must be looking at FFI. One of the things I want to talk about is this. We talked about string, and we talked about string slice, and also OS string. But I think the most important thing is string and string slice, because if you're writing plain Rust, those come up quite a lot. Well, maybe my first question, let me just throw 2 questions at you, right? How do you properly pronounce the string slice? Because it's always ampersand str. And the second question I have is when would I choose one over the other? And why do we have 2 also?
Yeah, that's a great question. And let's see, pronunciation. I guess I usually say string slice and heap string to disambiguate between the 2 different things. And the difference between them, and this is actually present in many, many types within Rust, not just strings, but the difference between them is a string slice is essentially a view onto a string, and that might be a string from any arbitrary point in memory. So a string slice is just a length and a pointer, and that's it. So this might be a string literal that you wrote within double quotes that's in the code of your Rust program. We call that a static string slice. It might be a substring of a heap allocated string. It might be a substring of a static string. It might be a substring of a substring of a substring of any region of memory coming from anywhere. Generally speaking, if you do not need to mutate, a string, then you should be dealing with string slices, because it's significantly more flexible than using a static heap string. Or sorry, not a static heap string. There's no such thing. Then as compared with using a heap string. So if you use the type, capital S string, that is a heap string. That is a string buffer which is always 100% of the time allocated on the heap with dynamic memory. It is the only way to have a mutable UTF-8 string in Rust in the standard library. I'm sure there's crates that have other string types, but that is the type we use for mutable UTF-8 strings. So if you need to append characters, append substrings, you would need a string. But if you're, for example, iterating over the lines within a file or an IO object, you would probably want string slices rather than heap strings. Because, for example, if you have say a 100 megabyte file and the whole thing fits into memory, you can read that entire thing into one giant heap allocated string. And then you can actually iterate over all of the lines just using string slices, because the whole it's kind of weird to talk about in words without code.
Well, because a string slice is basically a pointer and a length, right? And so you would just you just iterate through, right?
Yeah, each string slice is, as the name suggests, it is a slice. It is a piece or a view of the big heap allocated string that's sitting out there. So, if you have a 100 megabyte file, you can look at each individual line without having to create a new memory allocation for each individual line.
All right, but now when we say line, what are we defining as a line? Is it every single new line character?
Yeah, I mean, this was just an example. So string slice is not necessarily related to new lines. You can hold as many lines of text as you want within a string slice. That was just, a common example. Somebody reads in a big file and they want to look at each line individually. You would look at each line as an individual string slice rather than a heap allocated string.
And I think for each one there's also a null byte at the end of the
No, that's not
line?
true.
No?
Rust strings are not null terminated. If you need a null terminated string in Rust, you would use the C string type, C string or CSTR types, which are heap allocated C strings, and views onto C strings. So similar to those other type. Oh, wait, no, you can't have a slice of a C string because it has to be null terminated. Yes, the difference is C string is an owned C string, so that's something that Rust will be responsible for deallocating, and CSTR is a borrowed C string, so that's something that Rust would not deallocate, and it will assume that C code is later going to deallocate.
So even somebody seasoned at you, it takes some time to think about all these. I'm just still trying to process everything. I also brought this up before the show. One of the confusing things that I was trying to wrap my head around is that there's this thing called, there's a module called FFI. There's a section, I think, specifically about OS. And then there's, of course, things like libc and these kind of shared libraries, which you can also bring in, which also have some kind of FFI piece. As somebody, if I want to just add Rust to my program, where should I start? And do I actually need libc? Can I use just straight from the FFI crate or FFI module within Rust standard library? Or what? I need some help over here because I'm getting lost.
Yeah, so I think it depends on what your host language is, basically. So for folks who are listening to this, who presumably are Flutter developers, I believe there's actually there are crates, which is a Rust term for libraries, which are specifically designed for integrating Rust with Flutter. So if you use one of those, it can handle a lot of the heavy lifting for you. And the name of that actually escapes me right now. I probably should have looked that up right before this call. But there are similar libraries which are available for other languages. So in my book, I actually have at least one chapter which is discussing using the Pi03 crate to integrate Rust directly with Python code. And the library handles all of the interaction directly for you. You can pretty much always drop down to CFFI as a lowest common denominator. But I would say that for most folks, using one of these libraries is probably going to be a bit simpler. But yeah, libc and the raw FFI stuff is generally an option that people can use if they need to do something that's kind of tricky or outside the purview of these libraries.
Yeah, I think I found one called the Flutter Rust Bridge.
Yes, that's the one I was thinking of.
Is that the one? Yeah. This one seems more like a code generator, which could be useful. Not too sure. But yeah, okay. But at least it answers my question. So I was kind of cheating and asking you questions before we had our show. I apologize in case that bothered you. But my question was if I have a U8 int list, what would that be within Rust? But then what would that be within C, right? Because you always have to write the C binding. So when I'm saying that, I'm talking about like if I'm using Rust to create that C bridge, I guess you would call it.
Right.
That would be that would be a pointer, right?
Yeah. So the okay. So the C equivalent types that you would write within Rust for that would probably be pointer mute U8, and that would be the pointer to the buffer, and then you would also need the length, which would be a usize. And then if you were writing actual C code, that would be like what is that type called in C? I think it's like uint 8t. So it would be uint 8t pointer and a size t.
So a vec u8 would translate to. Sorry, I'm trying to wrap my head around this. Okay, so but a vec u8 is owned, right? So actually there'd be some copying happening.
Yes, you could also construct that as a slice. If you were just borrowing the data and not mutating it, you could use a slice from raw parts, which you could also construct from a pointer and a length. And then I think actually that would be the preferred way to do it. And then if you wanted to reallocate, you could use slice to vec to reallocate the slice as a vector. But if you're not mutating, then it's not necessary. If
I'm not going to be mutating, though, you said I should use a mutable pointer. But if I'm not going to be mutating, I could just use a const pointer.
You can use a const pointer. Yep. I believe the slice API allows for using a const pointer to construct a slice. I could be mistaken, but I believe that's allowed.
Well, I feel blown away right now trying to think about all this stuff. Like, I think when I saw the syntax of the FFI in your book, I was a little bit blown away. Like, what does this even mean? So I think you have const star and then pointer. I can't remember off the top of my head.
It's actually pointer const asterisk const u8 is the Rust syntax for that.
Okay. I think I have to look it up to actually remember this, but I'll take a look later on when I go back to this stuff. But it's quite interesting. I think I need a moment to kind of catch myself because when I'm thinking about trying to go back and forth between it's difficult. But okay, I appreciate that.
Yeah. I could talk about like why I got interested in this and why I had so much experience doing FFI previously. Ironically, and I would certainly not recommend this to anyone, but the first Rust project that I was actually paid to do was an FFI project. I was working at Kroger, which is a grocery chain in the U.S., and I was working on a DevOps team, which is a fantastic anti-pattern. But we were responsible for setting up a canary deploy system for the rest of the teams at the company. And we had gone down one route using a tool called console template, which regenerated the Nginx config files whenever data in console key value store changed. And somebody on the team did heroic debugging work to figure out why this wasn't working for us. It turned out to be related to disagreements between Nginx and some HTTP clients about how session termination needed to happen. But the end result was we couldn't use config generation to do what we wanted. And I don't remember if it was me or somebody else who proposed, what if we did this like dynamically within Nginx itself? So using Nginx's memory space and process space to do this dynamic routing choices, then we wouldn't actually need to edit the config files. We wouldn't need to refresh the processes. We would just keep the same processes running, and all the requests would go out through the processes. So the very first Rust project that I did as a part of my job was actually to write a Rust plugin for Nginx that did dynamic routing decisions based on a console key value store. And this is a very bad first Rust project because A, it's FFI, which is inherently complicated. B, it's FFI with Nginx, which does not have a very well documented C API. I'm sorry if there are any Nginx developers listening, but the C API for writing Nginx modules leaves a bit to be desired. And I spent a lot of time just reading the C code for Nginx to try and understand ownership rules, the process lifetime, and all this kind of stuff. But it gave me a great opportunity to learn a lot about how Rust worked at a pretty deep level, how FFI worked, how to lay out problems like this. And I think in the advanced FFI chapter of Refactoring to Rust, we do actually guide readers through creating their own much simpler Nginx plugin from Rust. So that was kind of the trial by fire that I had.
I think I stopped at that section. I didn't keep going after that, but because I became busy. I had only had time on the weekend last weekend, and it was quite good. But yeah, that part also kind of made my brain start to melt, because like when you have the Bindgen, I was like, oh, okay, that I need some time to digest all this and take a look at it. Because I was just reading it. I didn't follow along with everything they're doing. Mm-hmm. Maybe if I was following along, it'd probably be easier for me to handle, but I just had time to kind of read as I was on the go. But I understood basically most of it. I think, finally doing it will probably cement everything. But that was a good section. I think it's also good to have the Bindgen. I've only done C Bindgen, where you actually generate the .h files, not the Bindgen. So that's good to know that you can use that style.
Yeah, I haven't actually used C Bindgen myself to go from... That is a tool, so that the tools we're talking about for listeners, Bindgen is a tool that will take C or C++ header files, and it will create Rust type definitions that match up with that C or C++ API. And conversely, C Bindgen will take Rust code, and it will generate C or C++ header files so that you can call your Rust code from C or C++. And I haven't actually messed with C Bindgen, just Bindgen, because I've been writing little Rust pieces that integrate with existing, C programs. But C Bindgen, I have heard, is a good tool that does what it needs to do.
Yeah, definitely. It was super useful for me. Sorry. So early in the morning over here, so it's about 9 a.m. almost. So let's see. Yeah, I think it's good to hear your background, because I usually ask this question, but I'm so interested in this topic that I completely skipped your background. But so you're working at a new place now, right? That's OneSignal, I think.
That's correct. Yeah, I'm working at OneSignal right now. I actually found OneSignal on a Rust jobs board when I was moving out here to the Bay Area a couple of years ago. We use Rust in several of our backend applications, as I mentioned previously. We use it for the core of our notification sending system, and it processes... I think we've seen it peak at like 6 million ops per second and around 10 billion per day, I think, mostly. It's a system that scales very well relative to the other parts of our stack. We've been really happy with Rust in that position. The previous thing we had was using Ruby and Sidekick. I think that system started to run into bottlenecking problems around millions of deliveries per day, as compared with might have even been millions per week, as compared with the 10 billion per day that we're doing today. So massive scale difference between the Rust and the Ruby version. And we also have some Kafka consumers that are written in Rust. And, we have some homegrown tools that help us to manage that. And that also works very well. And we have some beautiful high throughput, low latency, low memory footprint Kafka consumers. Thank you to Rust.
Yeah, Rust is an amazing tool. I find it funny that a lot of people want to go to Go. But for me, once I saw some benchmarks from, what's it called? This is a long time ago. This is Discord. Where they basically said, listen, we optimized as much as we could, no matter what. GC killed us, and we went to Rust and never looked back since then. I'm thinking that's really the power where it's at.
Yeah, so Go, Rust is compared with Go a lot. I think they occupy a similar space in, lower level than Python, Java, whatever languages. Systems programming tools are commonly written in Rust and Go. Servers are commonly written in both. We actually use Go at OneSignal as well, and we like it for certain use cases. But I have heard, and I apologize to whoever I heard this from, but the comparison that I've heard is Rust is one of the easiest hard languages, and Go is one of the hardest easy languages, because sort of the pick up and start doing stuff is very hard with Rust because of the borrow checker. But like once you get past that hurdle, it's really easy to do stuff that's scary or hard in other languages, like FFI, like parallelism, like memory reuse. Whereas Go is very easy for new people to pick up. There's very few keywords in the language. The API surface of the language itself is very small. So it's easy for folks generally to look at a Go project that they've never seen before and figure out how it works. But there are so many foot guns in Go, right? It's so easy to not check the errors when a function returns. It's easy to create race conditions from Go routines. It's easy to create too many Go routines and cause GC problems. What's the other one? There are many surprising things about the way Go language actually works. Like if you have an interface type comparing it with null isn't actually comparing it with null. Like if you have an interface type and the type is known, then it will actually never compare. It will never be equal to null, which is very strange. I was very surprised when I learned that for the first time. But yeah, there's just a lot of little things in Go that will like sort of bite you as you go along, as you get more advanced with the language. But it's easier to get started with Go, harder to get started with Rust. But I think, easy to learn, hard to master versus hard to learn, maybe easier to master.
I think another important thing you forgot about, which I've always seen people complain about in Go, is that Rust has generics. Go does not.
Yeah, so I think they're adding generics to Go in some upcoming version. I don't know what the timeline of that is, but I have played with the like experimental new version of Go that gives you generics, and as expected, you can use it to write data structures. You can finally write a map function in Go. It's that's nice. And I think some fairly high profile Rust person recently designed a theoretical sum type for Go, which is similar to Rust's enums. So if this were adopted, this could theoretically allow for results to take over in Go and replace the current like error checking mechanism that exists there. I think there are other proposals as well to streamline error checking in Go. But the current system, it's kind of verbose, and I don't know if it's easy to misuse, but I kind of want to skip my error checks in Go because you have to write a lot of code to do them.
Yeah, there's always you get the assignment from a function, and like you can always prefix error with the underscore and just forget about it and keep trying to go.
Right.
Which works in POCs and prototypes, but after that, you really need to go back and fix all that.
Yeah, absolutely.
Okay, I think I kind of abused you too much for my own personal needs, but I'm thinking a lot of questions I think that beginning Rust developers also have, like the string slice and string. What's the difference? If I don't have UTF-8, what can I do? There's OS string. There's other methods, so don't worry too much. Yeah, is there anything that you really wanted to say before we start to sign off?
Well, along those lines, what you were just saying for new Rust developers, I would encourage you to not care so much about the theoretically perfect type for you to be using. This sort of ties in with what I said in my RustConf 2021 talk a couple of months ago. it's very easy for Rust developers to get like swept up in making something that performs as fast as possible, just because the language does make it possible to do lots of optimizations that like make you feel good and make you feel smart when you pull them off. But Rust is a fast language, and you don't necessarily need to worry about saving every possible allocation and using the lowest memory possible types. So, if you're a new Rust developer, don't be afraid to use a heap allocated string. Don't be afraid to use clone to copy values. Focus on writing something that works first, and, you can clean it up later. You can make it fast later. But if you can't solve a problem slow, you probably can't solve it fast.
Yeah, I love this advice. I think when I did the Rust Station podcast, somebody else also gave this talk. I think it was Luca. And that's an important thing. Don't worry about optimizing until it's really a problem.
That's right. And I also spoke last week to a Rust meetup in Oslo, Norway. It was actually it was a talk about optimization. So I did go into some like nitty gritty details on things you can do. And it was a really interesting talk that I'm going to be uploading to my YouTube channel in the next couple of days. But I heavily prefaced it by saying, be careful. Don't do this first. These are not best practices. New people, don't worry about doing this stuff. This is like fancy stuff for when you actually you need to exploit all the possible performance. And then the other piece there is you have to if you're at the point where you're trying to optimize for performance, you have to be measuring performance. You have to have a benchmarking suite, or at least, some mechanism of measuring runtime or, throughput of your program, because if you're just applying optimizations blindly with the belief that you're making your system faster, I think really all you're doing is trying to convince yourself that you're very smart by doing these neat tricks. Like when I was in the process of optimizing something, I made optimizations that they thought would make the system a lot faster, and they actually made the system slower. So you have to be measuring for performance if you're doing optimization. Like, you shouldn't just be saying, "Oh, well, I can remove this whatever allocation and save 5 cycles on this CLI program that already runs in 10 milliseconds." Like, who cares?
Yeah, I think most of the time this kind of stuff doesn't really matter. But if you're doing like embedded development with a really crappy CPU, then maybe it's really worth it. Depends kind of your situation.
Or if you're processing a lot of data, in this optimization case that I talked through last week with the Oslo group, I took a Rust program from what did it start at? I think it started at around like 13 megabytes per second up to like 190 megabytes per second through optimizations. And that includes adding parallelism, so that's not just from removing allocations. So there are meaningful performance benefits that you can confer through optimizing and through doing tricky things. But it's also worth pointing out that the Python system that I was trying to replace was operating at 500 kilobytes per second. So my very naive Rust version that wasted a lot of memory was still, almost 300 times faster than the Python code.
I think I remember Python said that if you ever want to go faster, you should always use CFFI. I think I saw that somewhere in the doc somewhere, or somebody talking about that.
Yeah,
so
you
kind of
probably shouldn't be worrying about optimizing raw Python code. And if you're tempted to use CFFI, I would say that Py-O3 is probably a better choice for you, because it's very easy to use Py-O3 to create extension modules within Rust.
Okay. I think the only thing is I had to say, please check out her book, especially if you're interested in bringing Rust to your Flutter projects or even any other project that you're interested in. It's a fantastic book. Of course, they won't go into Py-O. I don't know if you go. I think you do go into Py-O3, right? Or do you not? You mentioned it for sure.
I am currently writing the Py-O3 chapter, so that will be available within the next couple weeks. Yep. So the book is currently in early access on Manning.com. You can buy it there, and you can either buy just the ebook, which you will have access to immediately, and you can read the chapters that are currently available, and you'll get notified when there's new content that's added. Or you can buy the ebook plus the paper book. And if you do that, you will get the ebook immediately. You'll get notified when there's new content. But the paper book is not going to go out until everything is finished and, it goes to the presses and it's all said and done. So that'll be a ways out probably.
Yeah. Okay. Yeah, but definitely check out the book. Like I said, I found it extremely useful and, it was very helpful for me. And, you brought some more insights to me about the string slice. So that was good.
That's great. Well, I'm glad that was helpful for you, Alan. Thank you so much for having me on the podcast today. It was great.
Yeah, it's really great having you on. I might actually have you come back because you always got so much interesting stuff, especially towards the end of your book, because I'm sure there's probably some more things I think that could be useful for people in the audience.
I certainly hope so.
Thanks for joining us. Like I said, I hope to have you back again soon.
Thank you so much, Alan.